I combined two sections in the book because I know you've heard of both of these things, so we'll just give you a quick reminder of how to do composition of functions and inverse functions. The first thing we're going to talk about is function composition. And I like to think of it this way. It's like you're taking an input, and so let's think of a number. Maybe we'll use the number 3. And if I input the number 3 into this f of x function, well, here's an example. And I do 3 squared plus 3. What is that, 12? So in goes a 3, and it mixes with whatever's in the F watering can, and it comes out a 12, yeah? And then what happens when we dump that 12 into this g of x can, and it gets mixed up with whatever's in this watering can? It goes 2 times that 12 minus 5. What is that, 19? And so what we would say is that the output from the f of x became the input for the g of x. So that's a composition that goes g of f of x. Or in this case, we did g of f of 3, right? We figured out that f of 3 came out as 12, and g of 12 came out as 19. So that's the idea behind the composition of functions. This is just another notation that means exactly the same thing. I actually read that little circle as a tiny word of, g of f of x. It's just a new function that's made by taking one function and using it as the input to another. So that's just kind of a representation of what's happening. We are going to look at some examples. For example, f of g of x on these functions. I like to rewrite it like this, f of g of x, and actually fill in that g of x. Now I know that f of x is the square root of x plus 7. So f of anything is the square root of anything plus 7. Let me practice this a little bit earlier this chapter. Can you simplify the square root of x squared minus 25? If that wasn't a minus sign, you could. But since that's a minus sign, you know, the best we could do is try to factor what's under there. And even that would be x plus 5 and an x minus 5. So you actually can't simplify that. So we've made a new function out of the composition of functions. We can do that too if we're just looking for a certain function value. This one is g of f of 9. Can you do f of 9 for me? F of 9 would be the square root of 9 plus 7. I think that's 10. And then g of 10, going to this function, would be 10 squared minus 25. Your answer would be 75. If you want to pause me and try this next set on your own, I think that's a good idea. G of f of x is what this says to me, so I'm going to do g of f of x. Oh, this one's super complicated, isn't it? So that means I'm going to take this entire function and I'm going to substitute it in for the x in the g function. What would that look like? 3 plus the cube root of x minus 3 cubed plus 1. But wait, don't forget there's also that minus 1 under there. And so this whole thing is this input spot right there. So instead of cube root of x minus 1, I did the cube root of the f of x minus 1. Now that one can be simplified, especially because we had that plus 1 and that minus 1. Can you simplify a cube root of something cubed? The answer is yes, you can. It would just be x minus 3. Oh, and we could simplify that even, right? A positive 3 and a minus 3 equals x. There's actually something really cool to say about functions where if you compose them, you get the original number back. So let's try this one. G of f of 9. G of f of 9. F of 9 would be 9 minus 3 is 6. 6 cubed is 216, I think. So 217. And G of 217. Okay, so 217 minus 1 is 216. And if I did that right in the first place, the cube root of 216 would be that 6. And 3 plus 6 equals 9. I kind of called that one because remember when we did G of f of x came out as just x? Well, that means when you do G of f of 9, it should come out as just 9. I could do G of f of anything. And even if I don't know how to cube the numbers, let's say it's 11. Do you know 11 cubed? Doesn't matter. Because once you put it through the f function and through the g function, they kind of undo each other anyway. And you just get that original number back. So you know what they call functions that undo each other? Yeah, they're called inverse functions. So here I have an example of two inverse functions, f of x and f inverse of x. That's how you read that. And they're both functions this time. Let's just fill out the tables. So if I plug a negative 4 into the f of x function, negative 4, I'm going to do my best here, 2 times negative 2, I'm just plugging each of these x values in. Okay, let's fill out the blue table. The blue table is for the f inverse function. So I'm going to plug in a negative 2. Half of negative 2 is negative 1 minus 3. Half of 2 minus 3. Half of 6 minus 3. Half of 10 minus 3. Half of 14 minus 3. Sweet. Do you notice anything about those two tables? Hopefully you notice that they're just flip-flops of each other, right? The x values are the y values, and the y values are the x values. That's what inverse functions are. They're completely the opposite of each other. Let's maybe graph before we talk intercepts. So I want to graph the red function first. Negative 4, negative 2. That's about all I can fit on here. So it's a nice straight line. And then the blue one claims to be the inverse. If you were going to predict what the inverse would look like, what would you predict? Like a parallel line, a perpendicular line? Let's find out. Negative 2, negative 4. 2, negative 2. 6, 0, 2. Okay, it's not parallel. It's not perpendicular. That was not as exciting as I thought. Okay, I actually know the answer. The answer is, well, what kind of points would be the same even if we switch the x and the y? Points like 1, 1, and 2, 2, and 3, 3, and 4, 4. It turns out that the line y equals x is the sort of reflection line. It's the reflection line of any two inverses. Crazy, right? The x-intercept for that red function wound up being, well, it looks like it's back at negative 3, 0, yeah? And the y-intercept I knew was going to be up at 6. How about my inverse function? The x-intercept wound up over at 6. The y-intercept, it looks like it's maybe down at 0, negative 3. Seeing what I'm going for here? Again, these functions are complete opposites of each other. So x-intercepts become y-intercepts, only with a flip-flop. Y-intercepts become x-intercepts. Domain becomes range. Range becomes domain. That's what it is to be an inverse function. In order to find an inverse function, we just want to think, okay, well, our y value is always going to be half of our x value plus 8. And if we do the exact opposite of that, our x and our y value should reverse. So that is the inverse. Now, we always want to get the y by itself because it's asking for the y value. So I'm going to subtract that 8 over. I could either divide by half or I could multiply by 2. That's how we find an inverse. We switch the x and the y, and we solve for y. And the inverse of an mx plus b is an mx plus b. This one looks a little more complicated. Let's see if we can get this one. So y equals 2x plus 7 over x minus 6. I'm going to switch the x and the y. Seriously though, this is scary. Alright, now we have to solve for y. Okay, I don't do fractions well, so I think I'm going to multiply both sides by y minus 6. So I can stop dealing with fractions. I'm going to distribute that x, even though it seems like a bad idea. I happen to have done a problem like this before, and I know that it'll work out. So sort of your goal is to get all of your y stuff on one side and all of your not y stuff on the other side. What I mean by that is I'm going to subtract that 2y over here, and then I'm going to add that 6x over here. I'm just rearranging so I can get all the y's on one side. And here's that final step. If I factor out a y, I'm home free. Are you seeing it? So our final step, just dividing by that x minus 2. Oh, and I could write that y value as f inverse of x now if I'd like to. That one was a little trickier, right? So the basic idea to find an inverse, and it kind of makes sense because inverses just have the x and y values totally switched. So we switch the x and the y, and we solve for y so we can have it in that nice function form.